Hello, today we're going to talk about morphisms of presheaves and sheaves, and in the next video we'll hopefully talk about sheafification. So let's start with a lemma. So let's take a topological space and a sheaf F on X, and the claim is that for any open set in X, the following map is injective. So let's call it row U. So this goes from f of u. So these are the sections of f here, not the global sections, but if we look at the open set U, and then we take the product of the elements in U and then the stalks at the elements in U. So I hope you remember what the stalk is. And we send S to so these are called germs, so the product of these germs. And the claim is that this map is injective. Okay, so let's prove this. So I claim that it's enough to show that for S in f of u, Sx equals to 0 for all x in X implies S equal to 0. So we assume that f is a sheaf of abelian groups or some modules or something. So some kind of abelian category, if you know what that is. But it would actually also work for sets or something like that. Okay, so, well, now we assume that, so Sx. So why is that enough? Well, let me just tell you. So Sx equals to 0 for all x just means that the right hand side is 0, and S equals to 0 means that this implies that the left hand side also has to be 0. Okay, so let's assume this. And, well, by definition of the stalk, there exists an open neighborhood V inside of U, which is a neighborhood of X. So if we have some X, so then such that S restricted to V is 0 restricted to V, which is 0. Okay, let me write this more like a 0. Okay, and, well, now we can cover U by such sets. So because we have this for all x, and then we use the first sheaf axiom. So we get that S has to be 0. So we have an open covering, and S agrees for all sets in this covering with 0, so it has to be 0. Okay, so that's the first lemma. Now let's define a morphism of presheaves. So a morphism phi of presheaves. So a morphism of sheaves is actually the same as a morphism of presheaves, just the only difference is that, so let's say we have from F to G, so a morphism of presheaves, we just require F and G to be presheaves, and for a morphism of sheaves, we require F and G to be sheaves. But the definition is for both the same, so a morphism, so if F and G are sheaves, then a morphism of sheaves is the same as a morphism of presheaves. Okay, so that, what is it? Let's at first phrase it in terms of category theory. So that's a natural transformation between these functors. So we have introduced presheaves as functors, but if you don't know what it is, that's no problem. Now we'll give a more explicit way to describe a morphism of presheaves. So this is a family of morphisms, so this could be homomorphisms of group, or, well, in which category so the sheaf is. So if it's a sheaf of abelian groups, then it's a family of homomorphisms of abelian groups, and so on. So of morphisms, phi u from f of u to g of u for u in X open, and we have some further condition, namely we want that for all inclusions of open sets we get the following commutative diagram, namely we have f of u goes to g of u, so this is phi u. Then we have here the restriction, maybe let's call it restriction f comma v. Then we have phi v, g of v, and then we have the restriction of g to v. So so this commutes, and note that here we have, of course, different restrictions as we have different presheaves. Okay, so that's already the definition. So let me make a short remark, namely that a morphism of presheaves induces morphisms on the stalks. So we get phi x from fx to gx for all stalks. Okay, and now we're gonna use these morphisms at the stalks. So namely, now we'll get a quite nice result. So let's take two morphisms of sheaves, and I claim again from f to g, and I claim that phi is equal to psi if and only if phi x is equal to psi x for all x and x. So if the induced morphisms are equal. Okay, and the proof is also not that hard. So this direction is quite clear. So if these morphisms are the same, then the induced morphisms are also equal. So that's clear. And now let's prove the converse. So we consider the following diagram. namely we have f of u, we have g of u, so that's just phi u, respectively psi u. Then we have a morphism, the morphism from above, so this rho u, so that was just sending to the stalks, so this goes to fx, so the product of the stalks. Similarly, we have, well, maybe I should call it rho uf, rho ug, and similarly we have the same map for g. And then we have also two maps here, namely the product of the phi x, and we have the product of the psi x. Okay, and now let's see. So we assume that phi x is equal to psi x for all x, which means that now these two maps are equal. Okay, so that's good. And now let me give you a short reminder. Namely, we've seen that this map is injective. So this means that these two maps are injective, but this implies that phi u is equal to psi u, and we can do this. We can consider this diagram for all u in X open, and so we get, so this is for all u in X open, and so we get that phi is equal to psi. And that's it. Okay, thanks for watching. I hope that next time we can cover sheafification, and until then, have a good time and bye.